So, okay, we were discussing about this stability in the atmosphere, and so we just discussed about one important thing, that is, I said that if we consider that the two situations that we have explained here, say if is, as you can see, is if the parcel, as I have said, that parcel begins to move, the parcel begins to move, and then at one point of time the parcel begins to sink down. So, if the sinking down, as you can observe here, this is how it would look like. The parcel would begin to sink, the person would begin to sink. So, you can see this, instead of say having to go up there, so this is how the parcel is moving up, the parcel is moving up at this point of time. At this point of time, as you can see here, at this point of time, this the internal parcel temperature, parcel temperature becomes fast equal to the external atmosphere, the internal parcel temperature becomes fast equal to the external atmosphere, and less due to the atmospheric condition. It becomes less due to atmospheric condition. In such cases, parcel will begin to come down, the parcel will begin to come down. So, this is what is known as the stable atmosphere. This should be what is known as the stable atmosphere. When the internal parcel temperature becomes fast equal to the external atmospheric temperature, and then it becomes less due to atmospheric condition, a typical change in the atmospheric condition. This leads to in such cases the parcel will begin to come down. This is known as the stable atmosphere. On the other hand, if this situation is like this, the parcel continuously, the temperature reduces in the parcel. Remember one thing, what I have said, both this parcel and the external environment constitutes of air and nothing but air. Is that clear? Parcel is an imaginary imaginary object. The contents in the parcel and the external environment are same. There is no difference. The same air is here in cases like this. Only in a situation we have considered that in this process there is no exchange of heat between the internal parcel environment to the external atmospheric environment. All right. So, here if this parcel continuously, even if you see here the situation begins like this, the parcel goes up and up, and here in such a cases, as you can see, the situation is this, that if due to atmospheric due to atmospheric changes, the internal partial temperature becomes internal percent temperature is always, if due to atmospheric changes, the internal partial temperature is always more than external temperature, the partial will continue moving. The partial will continue moving. The partial will continue moving. This atmospheric condition is known as unstable atmosphere, will be known as unstable atmosphere, What is the significance of physical significance is this? The physical significance is this. You know, suppose here, say, if you just try to observe the surface of the earth, here in case, if you just observe the air, the hot air beginning to go like this is where the hot air would begin to, depending on how hot the substances are, they will form a pattern like this. This can be thought of in 3 dimension. This is what is, then this is what would be known as a stable environment. This would be known as the stable environment. So, you know, you can see here, this is a stable stable atmospheric condition, the stable atmospheric. On the other hand, if this is like this, if it is continuously moving, particularly the air parcels or the column of air or whatever you think of, the air current, if it continuously begins to move like this, this would create a greater amount of turbulence. You can see this particular environment is less turbulent in nature, because of this is where it would come to equilibrium very soon, whereas in this atmospheric condition the equilibrium is not being reached ideally within certain time, within certain altitude. So, this one would remain as an unstable environment. So, this atmospheric, you know, the particles or the gases that would be dispersed here, the gases would continuously be beginning to disperse and they would continuously begin to move. So, it would just begin to, within the atmospheric column itself, it will be continuously begin to move, and as a result of due to wind direction and things like that, this would be much more spread, you know, it will be a further more turbulence. So, here you can see less turbulence, high turbulence. So, this is less turbulence, high turbulence. So, this, as you can see, this has a great implication in terms of this has great implication in terms of this has great importance in terms of the particularly the stability of the air, as well as in understanding the dispersion of the pollutants, because as you can see, if it is a less turbulent situation, our estimation would be is in a position to be more correct than that of the estimation in case of unstable environment. So, this is a stable and unstable environment. Meteorologically, when we see this is what actually it means. All right. Now, here is this, having gone from that, there are many more things to discuss on this, but we will go to a new topic now. I would ask you to further read on this, but there are new topics that we can say is the temperature inversions. Temperature inversions. Temperature inversions is essentially, as you will see that, the temperature inversion signify the situations when the temperature inversions signify the situation when the atmospheric condition does not adiabatic lapse rate, does not follow adiabatic lapse rate, that is the temperature does not drop at a rate that is adiabatic lapse rate. Adiabatic lapse rate, the temperature does not drop at a rate with altitude. Temperature does not drop at a rate with altitude. Let me explain this. Adiabatic rate does not, or at an altitude like this. What we see now is this, in a situation like this, what is particularly, there are two types of temperature inversions we are generally commonly known. One is the radiation inversion. Radiation inversions take place due to nocturnal or the night time cooling, of the Earth's surface of the Earth's surface, especially in the clear winter nights. What happens is, I will come back to this, but just to mention the difference here, that take place due to nocturnal or nighttime cooling of the Earth's surface, especially in the clear winter nights. This is radiation inversion, and the second one is, I will come back to this again. The second one is subsidence inversions. The subsidence inversions are the result of the compressive heating of descending air masses in the high pressure zones. High pressure zones. Subsidence are the result of compressive heating. I will explain this compressive heating. Let me go back to radiation inversion first. Radiation inversion. What is happening in the radiation inversion like this? So, if you remember the way I have said this in adiabatic lapse rate, you see something like this. This is what okay. Say, considering this, say if you are just say height, say altitude and temperature. Suppose this is what is the adiabatic lapse rate, or say it's a close to adiabatic lapse rate. This is what is the close to adiabatic lapse rate. This is adiabatic lapse rate. If you remember the drawing that I have made, this is the adiabatic lapse rate, which is like this. If this is the adiabatic lapse rate, what we observe this is, as you can see, that with altitude, as we are closer to the atmosphere, the temperature is generally higher than that of at the height. Okay. What happens here is, particularly during radiation inversion, during the night time, this is during the night time, you can see here, this particular inversion takes place. This is how it would take place, the inversion. This is instead of following this adiabatic lapse rate curve, the curve would change like this. What it means is, let me explain this first. This one is, at about 9 p.m. At about 9 p.m. At about 6 p.m. it would be further closer, 6 p.m. and about 3 p.m. we will find something very close to adiabatic lapse rate, which is very close to adiabatic lapse rate. What is happening here, you try to understand this. If you just observe this now, earlier in this case, suppose this altitude here, suppose you just see the two cases here. This is the time, these are the 2 points. At 3 p.m. you observe them to be at this point, isn't it? Say about this point, right? At this point, this is the temperature. Say the temperature, as you can see, with the temperature is decreasing with altitude, as you can observe now. On the other hand, just try to think of this here. If it is crossing at 2 p.m. on at about 2 a.m. At about 2 a.m. what we observe is something different. Here the temperature is essentially increasing with height up to a certain elevation, and then again it would be following the adiabatic lapse rate. You see these 2 points here at the same height. This is say H1, this is say H2. Here we can find, say this one is T1 dashed, say T2 dashed, T1 dashed. This one is T1, this one is T2. What we observe here is T2 is more than T2 is less than T1. See, T2 is less than T1. Whereas on the other hand, we observe that yes, isn't it? This is what is called the inversion. This particular the change from the adiabatic lapse rate, the change that takes place is known as the inversion. So what we are observing is just like this. For about 2 a.m. in the morning, at about 2 a.m. in the morning, since there will be an effective way, nocturnal cooling takes place on the surface of the earth. The earth's surface becomes cooler than that of the air on top of it. Okay, but this reduction, this characteristics begins to change after 2 a.m. it becomes the most pronounced effect. After 2 a.m. about 9 p.m. 9 p.m., 6 p.m., 3 p.m. we can observe this would remain like this. But on the other hand, in the 3 p.m. side, as you can see, we will observe that it would almost be close to adiabatic lapse rate. This is known as the radiation inversion. This radiation inversion, there is another kind of radiation inversion that we generally observe, for your example here, that is particularly in the situation of, in the case of say height, this is altitude, and temperature. If you see altitude and temperature, we observe that at about 10 a.m. the inversion is like this. It's about 10 a.m. at about 10 a.m. Whereas the adiabatic lapse rate is essentially this one. This is what is, these are the things that take place. These are the things that are known as the inversions. These are known as radiation inversions. These are known as radiation inversions. These are quite prominent, these are quite prominent, and as a result of this, you can see this, the temperature, the comfort level increases. So in that about this time you can see this, the temperature inversion taking place like this, and particularly it is most prominent during the daytime, 2 a.m. say about 2 a.m. in the morning, we can find that the most pronounced effect of radiation inversion, and as a result this is perhaps the time when it is very comfortable for all of us to the temperature essentially on the surface of the earth on a particular day becomes coolest during 2 a.m. in the morning. Okay. So, this is called the radiation inversions. These are called the radiation inversions. These are called the radiation of inversion. The importance of radiation inversion is the importance of radiation inversion is to suggest during the winter evening, because of the importance of radiation inversion is to suggest the high incidence of pollutants during the winter evening because of lack of upward movement of the pollutants. The pollutants do not move because of, as you can see, during that particular time or during that particular time, the temperature, the surface temperature becoming low, the parcels would lose their heat content within a very short distance in the atmosphere, and as a result of which this would not be able to move up, and this would remain confined in the atmospheric, near to the atmosphere. At the same time, the same situation does not take place during the case of during the summer situation, the summer condition, when the summer condition particularly, as the temperature from the surface of the earth, becomes generally hotter than that of on top of it. So, there would be generally a gradual rise of the parcels in the higher atmosphere. There would be pollutants, but the most important thing is to understand this is that near the surface of the earth, most of the plant kingdom, most of the animals and men all exist. So, it is important that if the pollutants after their discharge disperse into the higher atmosphere, this would not expose the people and the population below, near the surface. So, we would always want that the pollutants take a travel instead of remaining fixed at one position. They take a travel, particularly during the wintry time when the temperature is very cold near the surface of the earth. The parcels containing the air pollutants cannot move up because much of the heat would be lost there itself, and they would begin to settle down there itself. So, this is what is the importance of this radiation inversions. This can result in different kinds of situations, particularly related to the pollution. So, this is So, is this is another is the subsidence. Subsidence inversions. The subsidence inversions, as I have already said, the are result of compressive heating of the descending air masses in the high pressure zone, in the high pressure zones. Here is basically a particularly this situation exists during a particular time of the year. You see, radiation inversion is quite common in throughout the season, throughout the year, but the subsidence inversions essentially takes place during a particular time of the year. Particularly, you say the subsidence inversions are quite common, particularly during the monsoon season, and particularly also particularly in European region or Europe or America, it is particularly during the summer. This is the subsidence inversions are quite common. In the subsidence inversions, the examples of subsidence inversions is a particularly this is in this say European summer. There are many. This is low pressure subsidences are low pressure subsidences. And high pressure subsidences. Those two things take place. Low pressure subsidence, high pressure subsidences. Low pressure subsidences are particularly that the temperature changes that is taking place during say particularly low pressure condition is say a 4 or 5 days during which time in the thick summer, in the hot summer, due to the formation of the clouds, due to different say typical is a what should I say, a random environmental change that takes place and causes the clouds to gather at different positions and to remain to rain for over the day, rain for throughout the day, days in the weeks and things like that. These are the particular situations which are low pressure subsidence takes place. That means here in the also the inversion would take place. The inversion would take place means the ground level temperature would be less than the higher atmospheric level temperature at certain positions. So this, whereas it should be other way around, if it has to follow the adiabatic lapse rate. So these are there are typical situations that take place this in the monsoon season in India, European summer. Also this is high pressure subsidence take place, low pressure subsidences, high pressure subsidences, just like that. They take place under this kind of condition. We say particularly, if you just see this, observe these subsidences. The subsidences are quite like this. Say is altitude, temperature, altitude and temperature. We can observe this, this is the subsidence inversions taking place, subsidence inversions taking place. European winter nights, particularly high pressure subsidence takes place, and the subsidence, you can see the changes that are taking place. This is the adiabatic lapse rate. This is the adiabatic lapse rate curve. This is adiabatic lapse rate. We can observe, say, in a night time, say particularly, is a low pressure condition, particularly in the low pressure condition, you can observe in the low pressure conditions like this. So, you can see this is altitude and temperature, low pressure, condition. So, you can see this inversions taking place at regular intervals at different points. Inversions are taking place at different points. Say here, as this may be, say here, this is, if this is, say this is the adiabatic lapse rate, this is the adiabatic lapse rate, this is the adiabatic lapse rate, and the inversion is taking place here. These are the inversions that generally take place due to this kind of situation, this kind of changes in the environment, There are few other things. On this. I would encourage you to read something from the books also, more details on this. But the basic phenomena is this. The basic phenomena is wherever the adiabatic lapse rate is becoming breached, the adiabatic lapse rate which should exist, this adiabatic lapse rate is either being violated due to different situation, different conditions in the different changes in the atmosphere. These atmospheric changes take place because of, say, diurnal variation, the daily temperature variation, nighttime temperature variation, atmospheric, other short term atmospheric changes like wintry, clear sky, absolutely clear sky. Similarly, on the other hand, in situation where it is the environment is the atmosphere is completely cloudy and rainfall clouds exist. So, in such situations, what we observe is that in most cases, either in the column of the atmosphere there would be the difference in the there would be changes in the temperature at different columns in the atmosphere, as you can see here, or this would be in the surface here also these changes can take place. Here you can see this is essentially, if it has to follow an adiabatic lapse rate, this should have followed like this, isn't it? But it has changed within the column of the higher column in the atmosphere, it has taken place. So, it has not. So, here in such cases, here this inversion is taking place within the two higher atmospheric columns. On the other hand, here it is, as you can see, at the ground level the inversions are taking place. The ground levels the inversions are taking place. In this count, just one simple thing that I would explain here is the mixing depth. So, what is this mixing depth as such is, you can see this, if you see a particular environmental atmospheric condition prevailing like this, this is a particular atmospheric condition that is existing. Remember this. At any time of the day or at any point of time, this is what it is existing like this. What we observe here is particularly this one is the unstable, this one is stable for a brief while, and this is what is they call is neutral. This is what is known as the neutral. The neutral is, neutral is a combination of stable and unstable atmosphere. In such a case, if you just see this is the adiabatic slab straight. If say this is the adiabatic slab straight, that is, this is the adiabatic slab straight. This particular point, maximum mixing depth. The crossing point of adiabatic slab straight and this is altitude and this is temperature, and the crossing point of alar adiabatic slab straight and the altitude temperature profile of the atmosphere is known as the mixing depth. This is the crossing point is called the mixing depth. The elevation means the maximum mixing depth. The product of maximum mixing depth and average wind speed the maximum mixing depth is the product of maximum mixing depth and average wind speed within the maximum depth is known as atmosphere's dispersive the product of maximum mixing depth and average wind speed within the mixing depth is known as the atmosphere's dispersive capability or also known as ventilation coefficient. That is maximum. This is given in terms of meter square per second. So here, what is this? Okay, we'll come back to this, but before I close this lecture, what I want to say is the mixing depth. Ideally, you just write down, ideally mixing depth signifies the zone under which the parcel and its constituents will temporarily reside. Signifies the zone under which the parcel and its constituents will temporarily reside. That is, or in other words, the zone of mixing and residence of the pollutants. Ideally, mixing depth signifies the zone under which the parcel and its constituents will temporarily reside. Is temporarily residing because all of them can settle, all of them can travel otherwise also. So, this is temporarily reside, or in other words, the zone of mixing and residence of the pollutants. So, if we are just trying to say, if we are just trying to observe, say, for a power plant, or for a power plant, this emissions are taking place, the mixing zone here would mean is the mixing zone would mean here till this point up to which the pollutants would reside, So, this is this zone is those are the maximum mixing depth, all right. Okay. So, this is what is this particular the characteristics of most of these meteorological aspects of air pollutants related studies. So, this would say what we have learned today is to observe what is the ideal atmospheric condition, that is to follow the adiabatic collapse rate, and in non-ideal cases like when there will be changes taking place. Ideal means, or in a particularly adiabatically ideal case where this temperature would go down with the elevation, but this would be violated because of different situations like daily changes, diurnal changes, nighttime changes, then seasonal changes, winter, summer, rainy season, all this would lead to, and as a result of which particularly related to this is, since in most cases the pollutants whenever they are being dispersed, either they are being discharged with a heat contained in them, say particularly a thermal pollutants, when they are leaving the stack, they have a temperature with them. So, this increased temperature would give them the buoyancy. So, this buoyancy and the atmospheric condition together would allow the particulates or the gaseous matter to reside in a particular zone. This zone is what we lastly known as the mixing depth, where they would reside. So, we will now try to see in the next class, we will try to see how it will travel, how long it would travel. That is what we would know as dispersion. Okay. So, we were discussing about this mostly the dispersion of pollutants in the atmosphere, and particularly today we will discuss about a very popular model which is used throughout the world, and in very research establishments, many research establishments where this the dispersion models of dust and other things are generally carried out. So we will see that in this lecture today how this distribution or the dispersion model is worked out, and what are its assumptions. As we know that any kind of model should have to have some kind of assumptions. We will also greatly in detail discuss about the assumptions that essentially are linked with a model, air pollution model similar to Gaussian plume distribution here. So we begin with the mostly there are few important things that we would just begin to discuss with before we actually come to this model. The first and foremost important thing here is the relationship between the height and velocity of air. The relationship between the height and the velocity of air. See here, this is what would be quite important for all of us. See, if you are just trying to understand the situation, mostly all our velocity measurements, air velocity measurements are essentially at the ground level. Say at a height, almost at most of the times at a height within 10 meters from the surface of the earth. So in such cases it is necessary to sometimes estimate what is the velocity at this height, 100 meters, and the temperature, reducing the temperature by 1 degree. So you find the plot. So if it is say 25 degrees centigrade here, and another point would be at say 24 degrees centigrade at 100 meter, isn't it? So this would provide you the this adiabatic lapse rate. This adiabatic lapse rate, if you just consider this, with this adiabatic lapse rate, if you just try to find out, there's the value here just like this, if it is the atmospheric temperature profile. This is atmospheric temperature which is actually available at the atmospheric, say this is the atmospheric temperature profile. This is the atmospheric temperature profile which is almost closely resembling to this adiabatic lapse rate in a situation like this. This is adiabatic lapse rate, which is an ideal condition. This is the atmospheric condition. Okay, this is called atmospheric temperature profile. Atmospheric temperature profile. If this is so, we can find the Plume model that we can observe here. The Plume would show a characteristic like this. The Plume would show, irrespective of the height of the stack, it would show a characteristics of the Plume would be like this. It would be like this, forming a clearly distributed pattern of, you see this one would be, there would be some changes in this. So but this would be, according to this one, is along the central line. It would be symmetrically distributed along a central line. This is central line. Okay, this is the distributed along the central line. This particularly would be in a situation like this is known as coning. This is known as coning. Atmospheric temperature profile, is connected with this ALR and atmospheric temperature profile when they are like this in a particular time of the day or in a particular season, when ALR and say atmospheric temperature profile are quite similar, or quite close to each other. In such cases, we will find the plume which would be discharged from the smokestack would have an identical distribution. In such cases, we observe that the particularly the smokestack pollution, the smokestack emission would form a plume which would be like this. It should be like this, since it would be just the other way around. It will find lighter. Here it was denser, which was being discharged from the atmospheric air. Here it is lighter than the atmospheric air present at that point of time, present at that place. So here it would be rising. So it is generally called as lofting. It's known as lofting. It's known as lofting. Okay. Now, having to say this, these are the typical characteristics that we observe in cases like the dispersion of these air pollutants across from emanating from a smokestack, emanating from a say the power plant discharges that you observe. Next time when you take a travel, wherever you find a power plant, you start to observe how these plumes actually behave. What you will find some interesting observations in that. Many of these cases you will find these patterns are being followed. These patterns are being followed. So what we begin to say from this now onwards is that as we can find out, we have found out that the different profiles that it would have. See, mostly this coning, looping, fanning, fumigation and lofting. So having to understood from here that we can go into the Gaussian plume distribution model, which goes like this. This particularly, beginning to understand this, it would require a certain amount of drawing here. Just as you can see, this would be okay. Let me draw it from here. This is what is smokestack. This Gaussian plume distribution is basically following the normal distribution.